wrap up the course by talking about gravitational instantons. So I always like to do one lecture which is sort of on essentially picking apart research paper or research papers. And I'd like to talk about this because it's something that I've been working on quite a lot recently in the context of the Higgs vacuum. So an instanton is, we've sort of seen all these non-perturbative solutions. We saw this domain wall, a string, and so we had this notion of these p-branes where we had a one brane was a string, the two brane was the wall, a zero brane was like a black hole or a point. And that's more or less as far as we can go in four-dimensional Lorentzian space. But if we're in Euclidean space, we could imagine a Euclidean spherically symmetric solution, which would then be sort of round in four spatial directions, and so therefore would just exist, if you like, in an instant in time. So that's why, hence the name instanton. So what are these, what are they and what are they good for? Well, they're an example of non-perturbative effects in gravity, and I'm going to argue that they're an example of non-perturbative effects in this pseudo-quantum gravity, in the sense that when we mean perturbative, we usually say something's sort of got this notion of an order h-bar term, but non-perturbative is going to be of order something on h-bar. So we kind of had a similar notion in these brane solutions where the electric ones were like perturbative and the magnetic ones were like non-perturbative. So the reason why we can even think about, when we say we want to think about quantum gravity, we always have to be a little cautious and decide what we mean by that if we're not actually doing some fundamental theory. So we're really talking about quantum effects in gravity. If we're doing perturbative quantum effects, we tend to fix our background and look at small perturbations around the background. So, what's a non-perturbative effect? That's kind of what we've got to access. What does that mean? And what we're going to see is it's actually describing a process of tunneling or vacuum decay. So that's sort of where we're headed. So I'm going to describe this in the context of some classic papers by Coleman and collaborators from the late 70s and early 80s. And I'll put the references over here. So what my aim is that by the end of this lecture, you can go to those papers and you'll be essentially able to follow them, or at least to work through them, because usually when you first start looking at research papers, it's a sort of, quite a brick wall quite often. So, tunneling. It's a really deeply quantum mechanical effect. In classical physics, if I bang against the wall, that's it. I can't go through it. Okay? But quantum mechanically, there's this notion that we can actually go through walls, at least in some sense, and with low probability. So let's kind of just recall our Schrödinger equation and the first time we meet quantum mechanical tunneling. We usually imagine that we've got some incident plane wave at a certain energy. So that's our incident wave function. Some of it reflects back, and some of it is transmitted. and we solve our Schrödinger equation. So we could put in that assumption, and we solve it at a fixed energy, because we've got a sort of stream of incident particles, and we use the boundary conditions here at the barrier. So this is a height v, to decide how to match together the various solutions. So we have oscillatory out here going to the right and to the left, oscillatory out here going to the right, and underneath the barrier we have two exponential solutions to the Schrödinger equation. So this gives us that our probability for transmission, which we can calculate precisely, so let me get this right, our probability for transmission has this hyperbolic sign in it, and it's dominated, this is the width of the barrier, it's dominated by an exponential. So obviously this is Schrödinger equation, it's not field theory. Gravity's never come anywhere near this so far. But it's getting across the idea that tunneling is something that is, although it can happen in quantum mechanics, it's a low probability thing. And its feature is it has this exponential form, sort of decay. So if I input my wave function here into the Schrödinger equation, I'm going to drop my M's and H bars very soon, but if I put this in, what you kind of see is that the dominant part of the of the sort of gradient operator actually comes in the phase, or the first derivative of the phase squared. So our equation of motion looks like the following. So this is kind of where we're picking out the main dependence of the wave function. So this kind of shows why you get the exponentials. So for v is 0, so that's kind of away from the barrier, you just get psi is plus or minus √2me, which is like the normal frequency. So you've got the I on h bar here, and that matches what you expect for the incident, sort of the incident wave function. Underneath the barrier, though, v is bigger than e. So psi is now imaginary, which shows that you get real exponentials. So that's kind of just sort of stating the obvious. So now let's just think about something. So at the moment, I've just started a completely new train of thought, but I'm going to bring the two together. Suppose I'm thinking about classical motion in a potential well. So here, a half x dot squared is some delta v. So if I sort of think, well, what would be the integral of 2 delta v with respect to position? Well, I turn it into a time integral by looking at this, and then I write that as the integral of delta v plus a half x dot squared d tau. Now that looks like a standard Lagrangian. It's got a kinetic and a potential term. So our exponent, so pulling these two lines of thought together, so normally a Lagrangian is t minus v, so the fact this comes with a plus sign means we've sort of inverted the potential. So in essence, I'm thinking take that tunneling barrier, I sort of look at a particle, it drops to the bottom, it gains a kinetic energy, delta v, it rolls to the other side, it comes back up, pauses, and then goes back again. So that's a sort of, it's completely fictitious. However, the action for that process happens to agree with the exponent that we want. So in this case, this is a fictitious process, but it's kind of linking this notion of the analytic continuation, looking at some classical trajectory, computing the action of that trajectory, and identifying it with the exponent you want. So of course, we've kind of already seen this idea of looking at Euclidean actions. We saw that when we looked at black hole thermodynamics. We had a partition function that was a sort of exponential of a Euclidean action. We had that dominated by saddle points, so we were looking for classical gravitational solutions. So that's a purely sort of gravitational entry into this thought, but I just want to show that even when you do just bog standard quantum mechanical tunneling, you've still got this tool. It's completely fictitious, it's a tool, but nonetheless, it's something that you can do to access the answer that you need. So in general, so for example, with alpha decay, radioactive decay, you've got this notion of something confined in the nucleus with a potential barrier, but it's actually lower energy if it's outside. So if you wanted to calculate this leading order sort of exponential probability of decay to get to a half-life, you invert the potential, you look at the Euclidean solution that kind of rolls up to here and then rolls back again. You compute the Euclidean action of that and take its exponential, and that gives you the probability of decay. So that's sort of what, if you like, one way of thinking about what goes on when you're calculating these Euclidean solutions. So let's now look at Coleman's work on false vacuum decay. So I'm going to assume I've got a scalar field, and I probably should have it a bit more enthusiastic, let's say, a bit bigger barrier. And I've got two minima in my potential, or at least two minima, one of which is a global minimum, and one of which is only a local minimum. So if you were over here, you could imagine at very low energies that if you quantize round here, you've got essentially what looks like a vacuum, some local vacuum with energy levels sitting round this base, but there's a small probability of exiting and going to the true vacuum. So we call this the false vacuum, and this the true vacuum. And it's the false vacuum because it looks like a vacuum, but it isn't. It isn't really the true vacuum of the theory. So what Coleman did was he considered a V of phi which was essentially a double well potential, but with a small tilt. So he's taking our standard double well here, and then it's tilting it with this linear term. So we have our notion here of epsilon being the difference in vacuum energy. So I've kind of cooked this so that phi is minus eta is, or roughly minus eta, is the false vacuum, and phi is eta is the true vacuum. more or less. So this false vacuum here is unstable, and the idea is that in order to get the dominant behavior of this probability for decay, you solve the Euclidean field equations and then compute the action. So that's kind of the idea. So first of all, I should stress at the moment we're not looking at gravity. We're just trying to see, does this make sense? Can we find a solution to this problem? So it means we need to solve the Euclidean equation. So I've just written down the Laplacian of phi, which has to be equal to the derivative of v. And now you can see how we're beginning to put together all of these different things that we've met over the last couple of weeks. You've seen what happens if you solve for phi with just this term. Remember that just had the tangent profile, and that was a domain wall. So by symmetry, we'll just look for a spherical solution in Euclidean space. So we're looking for a solution in terms of our Euclidean rho, distance from the origin, and we guess that it's going to be close to this wall form. So when Coleman was studying this in the late 70s, computers were still not particularly fast. And of course, physicists didn't use computers. We used pen and paper. So you just, obviously, this is an ODE. You'd probably just ask Mathematica or Maple to solve it now. No problem. But back in the day, that was not an option for Coleman. And so therefore, what he did, so this is these can be quite useful analytic techniques, is he said, right, we're going to look at a potential which is very, very close to one where I know the solution. And so I'm just going to say that this leading order behavior is going to be this domain wall, this tangent solution. And I'm going to go through and calculate what happens and then check if that is self-consistent. So in other words, you solve the leading order, you see what is the effect of a perturbation. Does the perturbation completely destroy your leading order solution, or does it just tweak it a little? If it tweaks it a little, then you know you've captured the essential physics. Sorry, I feel I have to send this message because you're all just so used to asking the computer to do it. So it almost feels like Star Trek these days, doesn't it? Computer, how does this? Okay, so what are our boundary conditions? We're going to sort of guess that phi is going to be roughly something like eta tanh root lambda eta rho minus rho naught. So this is rho. So that's our guess if we're trying to solve the equation. Actually, Coleman didn't even do that, at least not in terms of the physical argument. But if you look at very large rho, phi goes to minus eta, which is the false vacuum. At rho equals 0, as long as this little rho 0 is sufficiently large, then at the origin, phi is close to the true vacuum. So that is indeed what corresponds to that picture. Can't believe it, I didn't write down Coleman's actual argument here. Crazy. Okay, I'm going to do something very risky. I'm going to just try and do it off pat. So Coleman's argument was So his argument was this wall is thin, so the bubble looks very much just like a bubble wall sitting at rho equals some capital R. So here capital R would be root lambda eta rho naught. Well, let me just say sitting at R because I've got a scaling in there. So to form the bubble, there's a cost, which is making the wall. So that means I have to take the area of the wall times sigma. Area of the 3-sphere is 2 pi squared r cubed, isn't it? And the gain in energy is going to be the vacuum energy difference times the volume, which is, I think, pi squared over 2, the volume of an S3, times r to the 4th. So when you want to think about a solution to equations of motion, you're doing that by thinking small perturbations. It's a stationary point in terms of perturbations of the action. Now, we got our equations of motion here by thinking about the sort of Euler-Lagrange process, small perturbations with respect to the scalar field. But I can replace all of that detail by the essentials, which is a bubble wall at radius r. So that's my essential. And then if it's a solution, the action will be stationary under variations of r. So that's the idea. And you can think of this as like a Goldilocks process. It's very like a standard first-order phase transition when you're boiling water. A bubble forms. If it's too small, it'll just collapse down. And that's saying essentially the surface area is too great compared to the volume inside it, the gain from producing the volume of true vacuum. If the bubble is too big, it's simply too expensive to form. So all we do to find the solution is consider the difference between these two with respect to r. So we're looking at 6 pi squared sigma minus 2 pi squared epsilon, and that's r cubed, and that's r squared. So that's when those two derivatives will be equal. So that tells me, cancelling off the r's, the pi squareds, the 2's, it tells me that r is 3 sigma on epsilon. So this is a very heuristic, but it captures the sort of physical aspect of what's going on. Now, if epsilon is small, r is big. So if I now look here, r is big tells me this lambda eta rho naught is big, or rho naught is big. If I look over here and say, if I replace here with my rho, this is phi double prime plus 3 over rho phi primed. And that solution solves with those two things crossed out. Well, epsilon is small, so I'm okay on this side. And 3 over rho naught is small, so where the bubble wall is changing, this term is small. So it says that this is a good approximation. If I now add in this epsilon term and this 3 on rho term, it's only going to change that profile a little bit. So you guys put it on Mathematica or Maple, and you will find that this is a very good approximation to the result. So then my action, called B. I always forget which way around this goes. I think it's gain minus cost, hopefully. So I simply evaluate the difference between these two terms. So we've got pi squared on 2 into 4 sigma r cubed minus epsilon r to the 4th. And so that's equal to 27 sigma 4th on epsilon cubed pi squared. That's pi squared on 2. So that's there we go. That's the answer. Is that what I got here? Yeah. So that's my action. That was actually the argument that Coleman used because he wanted to kind of bring out the physics of what was going on. So the idea that bubbles can form, it also tells you why you expect the bubble to be spherical, because what you're doing is you're having this competition between surface area and volume going on, and we kind of know that spheres are the most efficient in terms of generating the best surface area to volume ratio. So that was also the basis for an argument about why these bubbles would be spherical, or dominate, or the process would be dominated by a spherical bubble. So that was Coleman's first paper. His second paper with Kurt Callan explored, obviously this is just the classical part of this process. If you want to actually calculate an amplitude properly, you have to consider fluctuations around the classical solution. So that was what they did, again, without gravity. So what Coleman then came back to doing at the beginning of the 80s was realizing that, of course, if you have vacuum energy, then you really can't ignore gravity because energy gravitates. So, again, at the time, this was, this was all relatively new, this idea about how to solve for these types of equations, including gravity. So first it was, say, 3 years after the Gibbons-Hawking paper on Gibbons-Hawking boundary terms and thinking about Euclidean gravity. Although, again, we can write down our gravitational equations, and indeed we did when we looked at the domain wall. We actually solved those gravitational equations. If we wanted to, we would just do it on the computer now. But again, at the time, that wasn't really an option. And so Coleman and De Lucia went back on this to this physically motivated argument of having this potential that was very close to something that was familiar, things that people were working on at the time. So this, with small epsilon, has a very thin wall. And people knew how to work with thin walls in general relativity because we have the Israel equations. And so Coleman and De Lucia could do this false vacuum decay with this thin wall to find a solution that was expressible essentially analytically. So what Coleman and De Lucia actually did was they found solutions for different vacuum energies on each side of the wall. So it wasn't necessarily going from positive vacuum energy to zero. They actually considered all the different possibilities. It's just that it's a very natural one to think about. And they found the solutions for the domain wall. And then in calculating the Euclidean action, the only kind of difference, or the sort of what you have to do, so if I can just draw some pictures and then say what the result is. The de Sitter space, Euclidean de Sitter space, so remember de Sitter space has a positive cosmological constant and its constant curvature. We analytically continue to Euclidean time. That's saying we have a positive curvature, constant curvature space. So that's a sphere. So that's our Euclidean background. So this is our starting point. This is our false vacuum. So that's replaced the field theory, original no-gravity picture of an infinite four-dimensional Euclidean space with something finite. So the radius of this, which is proportional, so remember in de Sitter space we've got in that lambda over 3 is equal to 1 over L squared. So the radius of this is proportional to 1 over 8 pi g epsilon, or the square root. So that gives us the radius. So the size of the sphere tells us about the vacuum energy. If epsilon's small, it's a big sphere. So if we're tunneling to 0 lambda, that's flat space, so that's just planar. So we have to, our bubble solution, the analog of this, is that I have to have inside the bubble flat, outside the bubble a sphere. So the way I do that is I take my sphere and I cut its nose off. So I hope that's clear. So this is my true vacuum. And my false vacuum and my wall. So that's the geometry. That is the bubble solution. Now you can do it via equations of motion, finding, what the size of that radius is. You're matching. We've sort of seen it with the, with the Israel equations. You're matching the inside of a bubble of Minkowski or Euclidean space, flat space, R4, to an outside, which is a sphere. And so you can do that with just solving equations of motion. There's also actually an analog to the Coleman argument here, because you could just say, I have a sphere, I have a flat bit, I have a bubble, I know that's of tension sigma, and I just sort of find, again, the cost and gain. So the only difference there is that the gain is not just the volume of the interior of a sphere in flat space, it's actually this cap that you've cut off. So you can do the same process, and you actually get an answer which is almost the same. So if I look at this, so if I look up there, it looks a bit different, right? But of course, the top has been written with no reference to gravity, whereas you can see a G on the bottom. So the first thing you should probably do is just check that this makes sense, that it gives you the same result as Coleman got when G goes to 0. So let's just check. So it doesn't go to 0. The first thing you might think is, hang on, you've got a G on the top. That's going to go to 0. But what you've got to notice is you've also got this L. So you have that G, so 8 pi G epsilon is equal to 3 over L squared. So that's our cosmological constant, setting the curvature of the Euclidean space. So I have to replace L with 1 over 8 pi G sigma. So you can sort of see that the G's here, this G L to the 4th, or rather G cubed L to the 6th, is going to turn into 1 on epsilon cubed. So on the bottom line, it's true that this is going to go to 0 as G goes to 0, but I'm still left with my 4 pi to the 4th. I've got G cubed L to the 6th. I've got a sigma to the 4th. I've got the pi floating around in front. And so I end up with 27 pi squared on 2 sigma to the 4th on epsilon cubed, which is, of course, the Coleman result. Now, of course, there's a lot of calculational detail that goes behind this, but what I wanted to do was to try and tease out what was the sort of essence of what was going on, so that, you can kind of see it's really, or if calculating this tunneling process is all about a balance between energy gained by making a transition to the false vacuum and the energy cost of producing the bubble wall. So that's kind of the gold standard when you're calculating vacuum decay. But as a gravitational solution, it's extremely special. You've got exact de Sitter space, which is smooth and featureless, and you've got this nice round wall. So maybe you could believe that squidging the wall a bit leads to a higher action solution, because after all, you've got this notion of surface area to volume ratio, but this is gravity. And if we think about our universe is not smooth. So why should we worry about this? Well, I'm not sure if you did this in the standard model course, but if you look at the running of the Higgs coupling and calculate how that runs with energy scale, the Higgs self-coupling receives corrections from loops coming from all the other particles, and the heaviest one, the top mass quark, the mass is perhaps the least well known. And so for the best guess values for the Higgs mass from the LHC and the top mass, it turns out that if you run the Higgs coupling to very high energy scales, it turns round and becomes negative. So again, I think it's only to within 2 or 3 sigma, but according to our best values for Higgs and top quark mass, our vacuum is actually not stable. It's metastable. So when this was first, this was sort of spotted as a possibility again back in the 80s, but just as a possibility. Now it's actually becoming more of a real possibility, but people weren't too worried, because you apply these arguments and you find that, like, the half-life of the universe is, 10 to the 139 years or something, absurdly large, right? But that assumes this form of an instanton. So a few years back, myself, a postdoc, and a colleague kind of thought, well, what happens if you add an impurity? Because in all cases, when you think of first-order phase transitions, they're almost always triggered by an impurity. So adding an impurity makes a phase transition easier to complete. So the obvious impurity in gravity is a black hole. So again, looking at things that we've done, we know what the geometry of a black hole is. We know what Euclidean black holes are like. So in essence, everything that we've done in the last couple of weeks, you've got all the tools you need to do this calculation. Now, of course, people thought of this back in the day, back in the 80s. So why didn't they get the answer that my collaborators and I got? And the answer, it comes in a technicality. Remember, when we did the Euclidean black hole for Schwarzschild, it had a periodicity inversely proportional to the mass. Now, if we have a cosmological constant, a positive one, so in other words, the Schwarzschild de Sitter space-time, the periodicity of tau coming from the black hole is not equal to the periodicity of tau coming from the cosmological event horizon. And so we have this mismatch between the natural periodicity that makes the event horizon non-singular and the natural periodicity that makes the cosmological horizon non-singular. And what that means is our Euclidean space has a conical deficit. And so that doesn't mean the bubble does, because you're sort of fitting together two different manifolds. You can always choose the local event horizon to be regular. But there is a process of subtraction going on, and if your bubble has got a regular Euclidean section, your background manifold in general will not. So you need to be able to integrate through these conical deficits. And that was kind of what people hadn't properly taken into account. So if I go back to my cost and say, why can this make a difference, this argument of cost and gain, the cost and gain argument. So the cost is again going to be something that looks like the tension times the area of this bubble wall. Now, our shape, our geometry has changed. Instead of having something that is O4 symmetric, we've now got something that's SO3 symmetric, the bit round the black hole, times a U1, the bit round the tau. So instead of having an R cubed here, I have an R squared and some sort of length of the time coordinate. Similarly, my volume is going to be R cubed beta. So I'm not putting the constants in because I'm only trying to sort of give an impressionistic sort of argument here. I still get that my radius is proportional, my critical radius is proportional to sigma on epsilon, but this now actually looks more like a 2 than a 3, but, you know, hey, 2, 3, that's not really that different. What's really different is the fact that the action now, instead of going like sigma to the 4th on epsilon cubed, it goes like sigma cubed on epsilon squared times this beta. So it's a different balance. So depending on the size of this beta, sorry, that's the temperature, delta tau is actually, goes like, sorry, pi GM. So dependent on the size of this beta, I could potentially drop this action. So what we did was we did the whole process, you know, in full of finding a thin wall answer and showing that, in fact, yes, it can drop this Coleman-de Lucia expression. And because the probability for decay goes like an exponent, if you halve the exponent, that's just a factor of 2 in B, it's a huge difference in terms of this probability. So therefore, having done the very sort of simple, relatively analytic version, obviously what you then need to do is to solve the full equations with the scalar field, with a realistic potential that you can sort of scan over sort of the range of the top mass, what the standard model potential looks like, and explore what these instantons are like for realistic thick bubble walls. So walls that are actually sort of what you would get from the standard model potential. And so, in essence, what our results are completely turn the process on its head, and sort of for black holes with m less than about, let's say, 7 Planck masses, So it's completely the opposite result. So we had to compare the probability of decay to the rate of evaporation, because if you're going to do quantum effects in gravity, you've got to think that the black holes can evaporate. And you find that if your black hole is like stellar size, then it does absolutely nothing. But it's possible that we could have primordial black holes that were formed in the very early universe, sort of from freakish overdensity in perturbations that are particularly overdense. And so these black holes, if they have a mass less than 10 to the 15 grams, they evaporate. And as they evaporate, they get hotter and they get lighter, so they evaporate faster. But this, the action for this B here sort of approximately has the form of a sort of... So what we're looking, we have a sort of remnant and a seed. We have a seed mass, a seed black hole, that's the seed to cause the decay. We have a remnant. So we've got like an M plus and an M minus across the bubble wall. And so our action is proportional to the seed mass times this difference in mass. And numerically, we see that this delta M doesn't really change very much. But as the seed mass drops, B is dropping. And because this is hitting in the exponent, it suddenly sort of becomes extremely relevant round about sort of 7 orders of magnitude above the Planck scale. So when the primordial black hole is, say, around a ton. And then at that point, given that it's much more preferred to decay, the decay is essentially instantaneous because, you know, it's faster than the black hole's evaporating, and the black hole's evaporating pretty fast by the time it gets this light. So it sort of took this, oh, we don't need to worry about it because the universe's lifetime is ages, you know, it's way longer than the universe, to saying, well, actually, if you have a primordial black hole, the decay probability is going to be instantaneous. It's very high probability. So you can view this as saying we don't have primordial black holes, or we don't have one in our past light cone. Or, of course, you could say, well, beyond the standard model physics. So it's just quite a neat example. We've got all the tools. You've got all the tools that we've covered in the course. But it's also something where you're bringing gravity in to an area where people don't usually use gravity and usually don't feel very comfortable with it, and saying that you get a very different result. So we've made it to the end of the course, in spite of snow days, and I hope, you know, at least I've given you some sort of survey of the different ways in which gravity gets used, both in a sort of very formal high energy sense, in the more speculative or phenomenological sense, and at least given some tools that hopefully will be used in the sort of follow-on strong gravity course. So I'll stop there